Today on How It's Made. Rawhide lampshades. Chocolate chip cookies. And MRI scanners. You don't need to have antlers over the fireplace to bring a touch of wildlife to your decor. A more subtle approach can be a lamp with a shade made of rawhide. Rawhide is untanned animal skin. The hide typically comes from livestock, so you get the decorative bang without firing a shot. You typically see rawhide lampshades in rustic settings, but they've also been known to add an eclectic twist to a modern decor. This company has been using the same techniques to handcraft rawhide lampshades since 1929. The first step is to construct the shade's frame out of 3mm thick steel wire. They begin by cutting the various lengths of wire to make the components for a shade of a particular size. Every frame has one top ring, one bottom ring, and several vertical ribs connecting the two. After clamping the wires alongside a measuring gauge, they position the blade where required and cut. They curve the pieces for the rings with crank-operated rollers, which apply pressure to bend the wire. It takes a few passes to work the steel wire into a full circle. Then they spot weld the ends together to complete each ring. They cool the hot weld in cold water. Now it's time to assemble the frame. They use a jig to correctly position all the parts. This one is for a slanted shade with an 18-inch bottom diameter. After laying in the bottom ring, they position one rib at a time and spot weld it to the ring. They assemble the spider, the inner structure of the top ring. They take a brass washer with 4 holes in it and insert a steel wire arm into each one. A single strike of a 1-ton press locks each arm in the washer. They spot weld the spider to the top ring. Then the ring to each rib of the frame. The frame is now fully constructed and ready to be coated with baked-on paint. This not only makes the frame more attractive, it prevents the steel from rusting as it comes in contact with the wet rawhide. The freshly washed sheepskin is the highest grade of hide available, so the color is an even butterscotch. Rarely any color variations or spots. They center the frame upside down on the skin, then work their way around, folding the skin upward and over, clamping it in place with clothespins. Then they flip the shade right side up and slit the skin at the top with a razor blade to release some tension. Now they sew the skin to the top and bottom of the frame with rawhide lace. However, this rawhide is cow skin. Once the sewing is complete, they cut off the excess skin. The rawhide is still quite wet, so they dry the lampshade in a heated closet for about 5 hours. When it comes out, they bathe the rawhide in a moisturizing agent, then a finishing solution, the specifics of which are a closely guarded company secret. These treatments bring out the butterscotch color and seal the hide, to prevent it from drying out and cracking. The lampshade then goes back into the heated closet for 24 hours. Lampshades are often hand-painted before this, in which case the finishing solution seals the oil paint as well as the hide. Each design is original and signed by the artist. A unique work of art designed to light up a room. Legend has it that chocolate chip cookies were invented in 1930 by an American innkeeper who ran out of baker's chocolate. She improvised by breaking a semi-sweet chocolate bar into small pieces. Instead of melting, the chocolate merely softened, dotting the cookie with chocolate chips. They look homemade and they taste homemade, but this home is a factory. Each ingredient goes into an industrial-sized mixer, starting with white sugar, then brown sugar, then butter, the mixer thoroughly blends these first ingredients until the butter becomes soft and creamy and the sugars are evenly dispersed. Then it's time for the headliner, chocolate chips. They're semi-sweet, which is a mixture of bitter and sweet chocolate. Next, flour, followed by baking soda to make the dough rise, and salt to add flavor. The final ingredients are whole eggs beaten, combined with vanilla, made from beans harvested in Madagascar, Africa. Mixing resumes until everything's well blended, which usually takes about 5 minutes. The company closely guards recipe specifics, but if you're curious, you could probably figure them out by multiplying the ingredients of a home recipe to the yield of a production batch. Workers transfer the cookie dough to a machine called the former. It pushes the dough through round dies, producing row upon row of round pieces weighing 1.4 ounces each, one of several sizes the factory produces. The factory then flash freezes the dough rounds for sale to food service customers such as restaurants and hotels, which bake the cookies in their own kitchens. The freeze tunnel uses liquid nitrogen to create the frigid temperature. The passing dough rounds solidify in approximately 5 minutes. Exiting the freeze tunnel, the dough rounds pass under a metal detector to ensure they don't contain any metal particles. This safety measure is standard practice in the food industry. The packaging system is entirely automated. The first station erects the box. The second station lines it with plastic. A conveyor belt, meanwhile, feeds the frozen unbaked cookies onto automated scales. Once a scale hits the per-box weight, feeding pauses, the bottom swings open, and the cookies drop into the box awaiting directly underneath. The next stations seal and label the boxes, which workers then load onto pallets. The pallets go into a storage freezer where they stay until it's time to ship them out by freezer truck to the customer. This company also sells gift tins of cookies online and by catalog. For that market, they bake the cookies in-house. Workers lay out the dough rounds 2 inches apart on trays lined with parchment paper. This prevents sticking, making it easy to remove the baked cookies without breaking them. The dough rounds are nearly 1.5 inches wide by 1 inch high. As they bake, they flatten out and double in diameter. The trays remain in the oven for 7 minutes at 300 degrees Fahrenheit. A turntable inside rotates them so that the cookies bake evenly throughout the tray. A few cookies per batch go to the quality control tester, who, unfortunately, doesn't get to conduct the assessment by eating the samples. Rather, the tester measures the diameter and height to ensure consistency in size and chip content. In the online and catalog order assembly area, Workers line the bottom part of the gift tin with a decorative cellophane bag. Then they carefully layer the correct number of fresh cookies inside in a staggered configuration. This not only creates a nice presentation, it also prevents damage in transit. They close the bag with a gold twist tie to seal in the freshness. Close up the tin, then pack it for shipping. This is how to give a gift of homemade chocolate chip cookies without ever setting foot in the kitchen. The MRI scanner was invented in 1977, and it has revolutionized medical diagnostics. Short for magnetic resonance imaging, an MRI offers an inside look at the human body without surgery or X-rays. When investigating health problems, it's a great way to get the picture. Using magnetic fields and radio wave pulses, an MRI can look right through you to determine what's going on under the skin. The magnet is incredibly powerful. It's up to 30,000 times stronger than the Earth's magnetic field. To make an MRI scanner, they weld aluminum casing around the magnet, creating a tunnel in the center for the patient. The seams must be extremely tight because the tube will also contain the super cold liquid helium, which will make the magnet so incredibly powerful. Once the welds are complete, they cap the magnet and transfer it to a test chamber. They pump helium gas into the tube and activate a vacuum system that sucks out the air in the chamber. A sensor confirms there are no leaks and the welds are tight. They now construct a second aluminum tube around the magnet. This will act as an insulating shield. They wrap an aluminized mylar blanket tightly around the magnet. Aluminized mylar was first developed as an insulating material for spacesuits. In this case, it will be used to deflect heat to keep the magnet cold. They now insert the magnet into a steel shell. This is known as the vacuum vessel. The air will be pulled from the space between it and the magnet, creating a vacuum which will serve as another insulator. They mask the MRI tunnel with plastic and spray paint the exterior white. The paint will protect the steel from rust. Next, they install a refrigeration unit known as a cold head. The cold head will maintain the helium around the MRI's primary magnet at the incredibly chilly temperature of minus 452 degrees Fahrenheit. This will keep the helium in a liquid state. Without the cold head, significant amounts would vaporize and be lost. They now pump the liquid helium into the magnet. It's one of the coldest things on the planet, and the fill nozzles turn frosty. Exposed to this extreme cold, the magnet loses all electrical resistance and becomes a superconductor, generating intense magnetic fields. With the MRI magnet complete, they move on to the gradient coil, which will control the orientation of the image with electrical pulses. It starts with a fiberglass epoxy tube cut to the correct length. A worker carves grooves in the tube and fills those grooves with epoxy. He then winds copper wire into the epoxy-filled grooves, and it adheres, forming the gradient coil. The team slathers epoxy onto the entire tube. The epoxy seals the wire, preventing vibrations of the coil when it's in operation. They layer etched copper plates onto the epoxy and they adhere. They wrap the coil tightly with Teflon cloth. A worker pours epoxy resin onto the fabric. He then winds tubing around the gradient coil, which adheres to the epoxy-coated cloth. These are cooling lines. They'll disperse heat generated by the gradient coil. Another worker now preps the next fiberglass tube. This one is for the MRI's radio frequency coil. There's much more to come before this MRI scanner is ready to provide an inside look at the human body. So stay tuned. An MRI scanner produces detailed images of bones, organs, and other structures inside the human body. It does this by generating a strong magnetic field that causes the body's hydrogen atoms to align and send a signal. The result is a picture that could lead to a diagnosis. Work on the MRI's radio frequency coil is underway. A technician attaches plastic risers and pads to the fiberglass core. The risers and pads will hold the circuitry parts at a uniform level. She applies adhesive-backed strips of copper from one band of risers to the other. These copper strips are the antenna. They'll send and receive signals from the body and relay them to a computer to produce the MRI image. She presses the copper with a round-tip tool for better adhesion to the core. She then dabs epoxy glue into the riser compartments. She inserts capacitors into the glue-filled compartments. These little capacitors will store energy and change the frequency of the coil to match the magnets. The technician solders the ends of the capacitors to the copper antenna as she builds the circuitry. She transfers numerous high-voltage inductor boards to the pads and screws them in place. Next up are cable splitter units. Another technician installs one near an inductor board. She routes some of the cables from the splitter to several of the inductors. And she solders the cables to the inductors. She places a plastic cable track on the side of the radio frequency coil and snakes the main power cable through it. She solders the cable to the antenna. The technician stiffens the copper antenna with composite boards to dampen vibrations when the MRI is in operation. She applies epoxy around all the cables. The epoxy secures the cables to keep them from moving around and making noise. The MRI's radio frequency coil is complete and ready to be put to the test. The next worker caps the ends with metal domes and bolts them tightly together. She pumps highly pressurized air into the capped radio frequency coil. She sprays soapy water over the exterior of the coil and looks for air bubbles. Bubbles in the soapy residue would indicate a leak, which would disrupt airflow in the MRI. With the radio frequency coil leak-free, they now slide it into the gradient coil, which has gained an outer fiberglass shell since we last saw it. The worker connects exterior tubing to the network of cooling lines inside the gradient coil. With those connections made, they're ready to assemble the coils to the magnet. The worker slides the assembly off the cart and into the MRI magnet. He installs a bracket that centers the coils, maintaining a small gap between them and the magnet. He equips the MRI with microphones and speakers to communicate with the patient. There's also a signaling system here for the patient to activate in the event of an emergency. Now for the ultimate test. They energize the magnet and send standard test objects into the MRI. They scan the objects and confirm the picture is clear. They add a metal and plastic outer casing. This MRI scanner is now ready to focus on diagnosis. The next picture it takes could be a lifesaver. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.